So if we have the circuit like this, so how do we design in Verilog? Yeah, maybe we do this together as a tutorial before we go to the next chapter. Maybe we take about half an hour to do this. All right, since we have still enough time for chapter 3. Okay, so if you use your computer, so you can have your computer switch on and open the Quartus 2. Right, so you need to have your full adder. Okay. And of course you need to have your Quartus 2 open to be able to write your code here. So first thing, we need to design our full adder. Okay. So let's design our full adder. So start a new project. So you can go to the new project wizard. All right. So need to have your folder. Maybe we create a new folder. We name it as comparator. All right, and maybe we name our design as comparator as well. Click select, click OK, and the name for the project is comparator. Just click next here and add files, because we don't have any file yet to be used in our comparator. Hold on, we need to have, or not comparator yet, sorry, we need to create our header. Yeah, this is half adder, or I need the full adder. So full adder, name it FA, and the name is FA. Right. So the file, we don't have any file to attach to this FA design yet. So just skip this. Next. And the device, if you want to use the hardware, of course you need to select the correct hardware, and in this case, because we just want to do simulation, actually you can click next here. So let the software automatically select the device for you. Right, and here IDE to setting, we will do the setting in later on. So just click next, and summary, just click finish. Right. Now we want to write the code for our full adder. So click new here and Verilog, click OK. So we have this, and we just write the Verilog code here. Module, the name is FA. So FA, what we have in FA, we have we name it A, maybe A input, B input, and C in input. Right, and we have output is maybe C and S for sum. Okay, done. And our input is A, B, and C in. Our output is C and S. Right, and we can design using data flow modeling, as we already have our equation for C and S. So S should be, we use the assigned keyword. This is uh, data flow modeling as equal to A XOR B XOR C in, right? And as equation for C or C out is C equal to A, we have A and B and C in, or A, not A and B, sorry, or A and C in, and we have or B and C in, B and C in, right? And done. This is our full adder, 1-bit full adder, very easy. All right, module. So we save our design here. Name it as FA, save, and we need to do the synthesis. All right, to create the net list. All right, let's the Quartus 2 to create the net list and make sure that we have no error. And here one warning, and the warning here, when you look at the warning, is actually regarding the license, so it should be no problem with our circuit. Except that our equation is wrong. Now it looks like okay, so we no need to do simulation here. We can go to the design of this comparator, right? So we need to create a new project. So we close the current one and have a new one. The name is the comparator. All right. So just select the folder, and the name should be the same here, comparator. So click next. Now the file that we want to use in our new design. Yeah. So remember that we will use the FA. Now we need to attach the file, or maybe you can attach in your design later on also can be done. But in this case, because we know already that we are going to use this full header, so just click this and add. All right, and good. Make sure that the file is here attached to the new design. Click next, and again the device, because we want to do the simulation only, so no need to select the device unless you want to use or want to implement in the actual hardware. So here you click next, and finish. Yeah, all right. And now we will have the new design. Name it as comparator, and what are the output in the output list. So we have how many? Let's see. It's the okay. Let's look at this. So we have X. Yeah, we have Y. We have CO, C out, and we have V, we have N, we have Z. All right. So now we have X, we have Y, we have C0. Yeah, in this case it's C0. Okay, no. So maybe it's C0. Yeah, X, Y, C0. we have V, we have N, and we have Z. Okay, so that's it. So input. So our input X is 4-bit and Y is 4-bit as well. Okay, and what about C0? V and Z is 1-bit. So you can input 1-bit. So all of these are 1-bit. So just copy this. All right. Input, and we have internal wire here, which is C1, all right, C2, C3, and C4. Okay, and S0, S1, S2, S3. So we can make this as a wire. C, we have C4 to C1. The name is C, right? And we have S, 0, 3 to 0 S, right? So this is exactly C1 to C4, C1, S3 to S0. Any other signal that we need? No. All right. So we can, okay, or you may have this signal. This signal also can, or maybe you include in the design also can. Okay, so now we need to instantiate this full adder, right? Using the structural modeling. So the name of our submodule is FA, all right? And let's say the first one we call it FA or M0, all right? M0, M0, and the port arrangement. Now we want to connect to this signal, connect to this signal, connect to this signal, connect to this signal, and connect to this signal. All right. So in this case is maybe C0. So we need to have the arrangement of the the FA. So let's open the FA. You want to here. Let me change the font so that you can see. Right. So we have A. Okay, make this smaller so that you can see this better. All right. Okay, so now A in our FA module, we need to connect to this, to x0. So here is should be x0, x0, and B in this case is we want to connect to y0, and it's actually y0 bar, right? Y0 bar for B. Okay, so in this case we can have not y0, right? And Cin is in this case is C0. So we can have C0, and C in this case is C1, and S is S0. Okay, so C1 and S is S0. All right, so this will be this part. All right, now we go to the second part. All right, where x1 is connected to A, y1 bar is connected to B, S1 is connected to S, and C2 is connected to C out, and this C1 is connected to C in. Okay, so we can have FA also, and because we use the same module, this one is renamed as M1, and now we have X1 and not Y1 in this case, and C in, our new C in should be C1 in this case, and the C out should be C1, C2, right, and S is S1. Okay, so that should be the case, and let's look at the module number 3. And the good thing about programming is you can copy and paste. All right, so FA, this should be M2, this should be X3, this should be Y3, and this should be 2, and this is number 3, right, and should be S2, correct? Okay, so here is C4, should be no problem. All right, so again we can use the same one, M3. The last model should be X3, should be why this is 3, should be 2, right? 2, Y2. Okay, this should be 3, should be 3, and this is C4, and this is S3. Anything else? Is it correct? X3, Y3, C3, C4, and S3 should be good. Okay, so it should be done. All right, so now we have all of these already, and we need to connect this C3 to C4 is an XOR gate to get overflow. So again, yeah, so we can use the data flow modeling to get that signal. So assign V is equal to what? To C3 XOR C4. Then we can add VSV. And now we want to get N. So N is actually connected to this. Yeah. S3. So N is very easy, connected to S3. And what about Z? So Z is connected to this. All right. This gate is NOR gate. So we can have assign Z equal to not S3 as 3 or as 2 or as 1 or as 0. Anything else? Should be done. And module. Right. So this is the design for this. Okay. So we save. Right. And we try to synthesize this code. Okay. Click here. Oh, got red message here is the error. So value cannot be assigned to the input V. Or do we? Yes, this is wrong, right? So V, N, and Z is not input; they are output. So before that, so we have the output. Okay, so this V, N, and Z are output, right? These 3 are input, and these 3 are output. Okay, synthesize again, and we should have no problem now. Yeah, there is no error and one warning, and of course the warning is for the license. Should be no problem. All right, so now we want to write the test band for this comparator. So you can write the test band by create a new Verilog code. Okay, so in this case, okay, so how to write the test band? So you need to have your time scale. So again, so use this character, yeah. So this character don't confuse with this one, yeah. So there are 2, the one that near to or beside your enter key is this one, and we need to use the one that near to your or below your escape key, below your escape key, right? For the time scale. Okay, and the first one is the scale that we want to use. So in this case, I use 1 nanosecond, and the precision is 1 nanosecond. So 1 nanosecond here means that after this, when I write the time, means that is referred to 1 nanosecond, or the step is 1 nanosecond, and this is the precision, means that this precision and the scale is the same here, right? So you need to have your module name for your test band, and let's say the name is now comparator test band. All right. Okay, and you want to have your test bench. Let's do this first. You want to run have your test bench. So what you need to do is this. So if this is your design, we call it this as DUT, or design and the test, and of course your DUT is your comparator. Okay, so your comparator, you have what kind of input? You have X, you have Y, and the output here is make it a little bit bigger. Okay, so you have V, and you have N, you have Z, right? Okay, so to do test bench, what you need to have is you need to instantiate this design to your test bench. So what you need to have is, let's say this is your test bench. Okay. So this is called comparator TB test bench. And of course, you need to have the connection to this. And let's say we name it as X also, Y also. And this one is another collection is V and Z also. Right? So you need to do this for the test bench and write the code for this one. Verilog code. Okay, so let's do that. So first things first is you need to instantiate your module in your Verilog code, and in test bench, this signal is declared as rec, not input. All right, and this signal, all right, V and Z will be declared as wire, right, for the test bench. All right, X and Y will be rec, and here will be wire, rec. So we can, not this one, we want this one, copy this one, and another one is rec. We have another one actually, this we have another input here, should be C0, right? C0. Okay, so this should be C0, and we have this should be declared as wire. So we have wire done. Okay, now we have all of this already, and we want to instantiate this one into our design, to this. So how to instantiate? The name of this one is comparator, so just comparator, and the name for the module, maybe we call it TB test bench. And now we want to do the port map, map the port. All right, so very easy. So we can use this one like this. Okay, same, and normally in test bench we use the port connection port map. We use the port connection rather than port positioning like this, because sometimes you may get error. So to be safe, use port connection where X is connected to X, Y is connected to Y, and C0 is connected to 0, V is just connected to V, and here N, and the last one is Z. Done. Okay, so Now what we want to do is to have the waveform. To have the waveform, so we need to have initial and begin. So we want to monitor and time. All right, and what is the signal that we want to look at? All right, so in this case, the signal that we want to look at is, of course, all of this signal, right? So we can just copy and paste here, and of course, we need to set that we want to maybe in binary. Y is in binary, or maybe hexadecimal, depend on your preference. In binary, maybe you can just copy and paste, right? Okay, and we need to have this again in here. It means that this is actually X, this is actually for Y, and this is actually C0, and so on. Right, and we need to end here. And now we will give the stimulus or the vector, the input vector, to our design. Yeah, so we need to use again right. Okay, so to have your stimulus, so you need to start with time 0. Okay, so this is how we write time 0. So time 0, what are the output, or the initial, not output, the initial input of our design? So in our case, we have how many input? We have 1, 2, 3 input. Yeah, so at time 0, so 0 here means that 0 second or 0 nanosecond in this case. X, yeah. Now X should be equal to maybe 5, right? Y equal to 4, maybe, right? And C0 is, if we look at our design, C0 now is always equal to 1. Okay, so we can have C0 equal to 1, right? And we want to change the value of X and Y, or maybe we start with 0, right? I think 0, 0, and 0, and the next 10 nanosecond, for example, and the next 10 nanosecond. So you can have here 10. Why I say this is 10 nanosecond? Because our time unit is 1 nanosecond. Means that 1 here represent 1 nanosecond. If 10 here means that this represent 10 nanosecond. So now we have change this to 5, 4, and 1. Okay, and again add another, the next 10 nanosecond. The next 10 nanosecond here means that the next 10 nanosecond means that if this is 0, this is 10 nanosecond, this is 20 nanosecond. All right, so we change this again to for example 5. The number is the same, maybe. Okay, and another 10, nanosecond. Maybe we change this to 3, and this one is 6 or 6, and this one is 1, and the next 10 nanosecond we stop the simulation, so we can have this stop, and you can have end here, and done. Alright, so these are the stimulus that we want to feed into the input, and we want to observe the output. Alright, so we want to feed this stimulus based on this timing, and we will want to see what happened to V, N, and Z. Alright, so we need to save this first. So the name is this, so just copy this and save. Click save, and maybe we check for any syntax error. Alright, so just check. There is no error, which is good. And we want to simulate. So we need to do some setting here, where we need to select the tools that we want to use. In this case, it's Model Sim Altera, and of course we use the test pen. So we need to click here, test pen just, and here this window, you click new, and the test bench name is this, and the file is this one. Add, and click OK. Click OK here, apply, and click OK. Everything is done. And now we want to do simulation. So to do simulation, just click this button, RTL simulation, because we want to see the functionality of our design. So use RTL simulation. Yeah, click, and you will have the model sim window later on. Okay, it's running on my computer now. Alright, so done. So this is the waveform. Can you see the waveform here? So maybe I change this to a decimal view so that we can see clearly. So we can see that if the input here, x is 5, and x, y, 5, 4, we can see that the v n is equal to 0, means that the number is positive, means that 5 is greater than 4, or x is greater than 4. X is greater than y. Yeah, negative. And 0, z is equal to 0, means that the number x and y is not equal. All right, but when the number is equal, x is equal to 5, y equal to 5, we can see that z equal to 1. Yeah, z equal to 1 means that x and y now is equal. All right, and when x is less than y, 3, 6, yeah, x and less than y, we can see that n is equal to 1 now, meaning that we have negative number here. 3 minus 6, we have negative number, means that x is less than y in this case. So this proves that our comparator is successfully created and worked well. Okay, so and we can see also there is no overflow here. All right, unless you have a bigger number, for example 5 plus 5, you cannot fit in a 4-bit anymore, so you have v equal to 1. Yeah, you can test that later on. All right, so that is how we design using Quartus. Yeah,